Hi, my name is JMcCulloch, and this is the Knowledge Integration 2 presentation for the three main classes of the junior year, EC 311, 331, and 341. We're going to start off by talking about the linear systems analysis aspect of what is happening in an audio amplifier and the speaker that is outputting the actual noise from the electrical signal that gets put in. So we're approximating a linear system here. So x of t goes into the linear system, comes out y of t. In our case, we're sending in a cosine. And so since we're sending in a periodic function and we're approximating a linear system, we expect to see a periodic signal coming out. When you put in a cosine, you actually split it up into its two components of the e to the j omega naught t and e to the negative j omega naught t. When you put those through the impulse response, you get out a certain output. The definition of h of j omega naught is the magnitude of h of j omega naught times e to the j phase of h of j omega naught. That's the two components of it. What we're dealing with is two of these, but at different j omega naughts. One is positive, one is negative. However, because of conjugate symmetry, for a real valued input, we have h of j omega naught equals h conjugate of negative j omega naught. So the magnitudes are actually the same here. So we can pull this out front, and it turns out that the output signal is just a, whatever constant you want to multiply it by, times the magnitude of h of j omega naught cosine of omega naught t plus the phase. So there is a phase shift in our output. Technically, this is not a nonlinear. This is a nonlinear system because of the diodes in the transistors. However, we are approximating a linear system to make it easier to analyze. In terms of 331 microelectronics, we are basically modeling the entire system as an easier corresponding system of linear elements. So you see here, this is our actual gain equation, which is composed of the gain of the first transistor, which is the voltage drop across the gate, and the collector, which is approximated by a current source and a resistor, as well as the second transistor, which is the same corresponding elements again. But the actual output is measured from the source of the second transistor. And so the gain ends up being the negative transconductance of the first conductor times the resistor in parallel with R1, which was a resistor in the actual circuit, which is multiplied by the resistance of the second resistor. So from a 331 aspect, it's much easier to analyze these circuits from a small signal model, which is what this is. So for our audio amplifier, the top line is for when our VB, if you remember from this slide, this is our VB, which is a DC current source attached to our actual sine wave for our Vn. So when we have VB set at 0.65 volts, we have this magnitude. However, if we raise VB to 0.7 volts, we actually have a decrease in the gain. So that means that the ratio of input to output actually decreases because of circuit elements when you increase the DC voltage. That doesn't mean that the actual output signal is weaker than this. That just means that the relationship between the input and the output actually decreases. So here we have our original 10 millivolt amplitude attached to our input signal. And we're dealing with a 1 kilohertz frequency. When we put that in, we have this small spike at 1K, and we have this spike at 0, which is our DC component. However, when we increase our Vin to 200 millivolts, we are actually creating harmonics in the system. That's the x squared and the x third elements of the Taylor series for the input. The magnitude of the DC input goes up, and the magnitude of the 1K dramatically increases, but we also have noise and distortion at multiple frequencies, which actually degrades the quality of the system in some cases. Now, for electromagnetics, EC341, we are dealing with mostly the actual speaker side, so not the amplification side. The speaker is composed primarily of the voice coil, which is a coil of wires wrapped around just a cylinder, and that is placed inside of a permanent magnet. Now, when we push current through those coils, it creates a B field in a certain direction. If we change the direction of that current, we also change the direction of that B field, which is from the coils, not from the magnet. However, when we put it inside of this permanent magnet, the B field, when they are in the same direction, then it's pushing in one direction, but when you change the direction of the current, the B field is actually attractive, so it goes the other direction. So that's how you create the oscillations in the speaker, which are kept in place by the spider so that it doesn't move laterally, it only moves vertically. And that is the end of my presentation. Thank you.